In this series of videos, we are going to go over some tools that you might have learned in either a number theory course or a discrete structures type course that are going to be really useful as we start our investigation of abstract algebra. And so this may be review for you, it may not be review for you, but because these tools are so fundamental to our study of abstract algebra, I want to make sure we have a very solid understanding of them. So in this first video, what I'm going to cover is something that I like to call the Quotient-Remainder Theorem, but I've seen written in other textbooks as the division algorithm. So just be aware of that as you're looking at a collection of different sources in order to master this content. Now to get the feel for what will be coming up in the Quotient-Remainder Theorem, I want to bring us all the way back to where this theorem really got used for us, which may be as far back as about 3rd or 4th grade for you. So what I want us to do is re-look at when we first learned division and when division problems were sort of simple. Now, not perfectly simple. I've got some examples here from about a 3rd or 4th grade math textbook called Singapore Math Books, which are really great books for teaching math. And I want us to look at not the easiest that division could be. Perhaps the easiest that division could be is when the division works out perfectly. So in this example, we're looking at having a certain number of eggs and then grouping them by dozens. 36 eggs would really be an ideal number of eggs for breaking into dozens. But when we had these 40 eggs, what I want us to go back and think about is we would put things into these whole collections of dozens, and then there might be some amount of leftover. And instead of trying to turn that into a fraction and talking about a partial dozen, we're just not going to do anything with what that leftover is other than indicate that it's leftover. So really how you would start approaching division problems once you move past that basic kind of division where everything just works out perfectly. Now, the examples on the previous page were great. They're an example of something that I would call measurement division. Just as a little aside, when you're talking about division problems, they can really be phrased in one of 2 different ways. And one of the ways is to say, I have some sort of number of objects, and I want groups of a particular size. How many groups are there? The phrase and the thinking that I want to use in this video for our example is thinking about a different type of division called partitive division, which is I have a certain number of things and I know exactly how many groups I want, and then I want to think about the size as something that's variable. So I'm going to use an example where we have hungry hippos, 4 of them to be precise, and then we have some sort of object that will be feeding to the hippos. So what kind of object will we be feeding to the hippos? Well, like any good math problem, let's start with some absurd number of watermelons. So let's assume that we have 27 watermelons that we're going to feed to some very hungry hippos. Let's assume 4 of them in keeping with the spirit of the previous picture. Now, we want to feed the watermelons to the hippos in a very particular type of way. I suppose rule number 0 would be to keep with the spirit of the first slide that we saw, that childish example of division, where if we have watermelons left over, we're not going to split those watermelons into parts to feed to the hippos. We're just going to let those watermelons be left over. But let's follow some additional rules also. Rule number 1 is, let's feed as many of these 27 watermelons to the hippos as we possibly can. We don't need a whole bunch of watermelon left over with nothing to do with it. 1 watermelon is often plenty. Okay? And the second rule let's follow is that let's feed each hippo the same number of watermelons. Maybe they're at a zoo, you want to be equitable to the different animals that you have at the zoo, and so let's do this following these rules. So again, to summarize, if the number of watermelons that we have is not perfectly divisible by the number of hippos that we have, we'll have to have some sort of leftover, and let's just let that leftover be. Then we're going to feed as many watermelons to the hippos as we possibly can while following that leftover rule, and we're going to be very fair. We're going to feed each hippo the same number of watermelons. So the question is, how many watermelons does each hippo eat? How many watermelons are left over? And I'll give you a moment to figure it out, but I have very full confidence that this is something that you can do. I in fact gave this task to my 7-year-old and she was able to do this and more in about 2 minutes. Full confidence you can do that, but just in case you want to follow along at home, the answer is that each hippo eats 6 full watermelons and there are 3 left over, which quite frankly is plenty of watermelon. Now, of course, the purpose of this exercise is not to practice over and over having 27 watermelons and 4 hippos. We're entering into an abstract algebra class, which is a class about generalizing and thinking of larger processes as opposed to specific examples. So the thing that I would like to do is say, okay, 27 watermelons was just a number that I picked out of a hat. Could this process that you did to solve the problem on the previous page always be done with, let's say, A watermelons? Are there any restrictions on that number A that you feel like need to be in place in order for this process to work? How about if there are B hippos? Maybe we don't have 4 hippos, we have 3, we have 10, whatever it could be. Are there restrictions on these numbers? Are they the same restrictions? Are the restrictions that you would put on the number of watermelons exactly the same as what you would place on the number of hippos? And for a more advanced thought process along these lines, if I change this example away from watermelons and hippos and just start thinking of things that I have to divide into a certain number of groups, does that change your answer if I take away the very specific context? Those are things we want to think about. Another thing we want to think about is, all right, we got an answer on the previous page. We had some sort of method of distributing the watermelons to the hippos. I got an answer. Very frequently in mathematics, we would like our answers to be unique, or we'd like to know, at least, if they aren't unique. So are we all going to get the same answer as we work on this problem independently? Or is there some other method of solving this problem that would produce different results? And last but not least, there are some other quantities that are going on here other than just the watermelons, the number of watermelons, and the number of hippos. There was another thing that was of particular interest to us in this example, which I'm going to call R, which is the number of leftover watermelons. That's another value. And in fact, is there anything we can say about the relationship between the number of leftover watermelons and any of the other quantities that we have running around on this page? The A, the number of watermelons, or the B, the number of hippos. Is there anything you can come up with about what must be true about the number of leftover watermelons?